This show was recorded on October 7th and 10th. You're probably watching this on or after October 14th. From where you are watching this, you know a lot of things I don't. It is, in fact, quite possible that you live in a world much better than I do. Your world is one in which you have watched an annular eclipse add a bit of excitement to your Saturday. You may have been weathered out, but even if you were, you hopefully got to see some amazing images taken by other folks with better luck. You might even live in a world that has one more asteroid explorer traveling through space, the Psyche mission on its way to the asteroid Psyche. As an aside, I want to say this may be the worst named mission ever for one simple reason. There are going to be so many parents and teachers who try to adult-splain that NASA would never name a mission the same as the world it is exploring. To all you children who are faced with that argument in your future, we are here for you, and once I was one of you. Anyway, as you watch this, I want you to take a moment to recognize that in a world that is in my reality blowing up my phone with breaking news alerts, you're sitting in a place that is just a little bit more awesome because of science. And I want you to enjoy that for me. Well, for past me, this me. Current me is hopefully also enjoying this moment. In this episode, we look at what tree rings can teach us about past earthquakes, how well machine learning can identify life, like trees, from carbon-rich materials that were never alive, to distant galaxies and spinning black holes. We even take a deep dive into antimatter. Not a literal deep dive, just a conceptual deep dive. This is Escape Velocity Space News, and I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. For thousands and thousands of years, human beings lived in mostly small towns and smaller villages scattered all across the world. When natural disasters occurred, they sometimes became part of local lore, but the details were often lost. In some cases, almost all memory of events was lost because there simply weren't enough survivors to pass the stories on. While humans may forget our past, the landscape sometimes retains records the local people couldn't. In a new paper in the journal Science Advances, researchers led by Brian Black reveal a bit of a horror story by reading the tales recorded in tree rings. Throughout the Puget lower lands are scattered lakes that formed when earthquake-triggered landslides dammed off streams and flooded forests. To figure out if these lakes formed during a single catastrophic event or a series of events over centuries, researchers used underwater chainsaws to cut sections of long-drowned trees. I would like to say I did not know underwater chainsaws were a thing. Every year, trees grow a new outer layer that reflects that year's growing season. Bad years will have thin rings, good years fat rings, and years with solar storms will have rings with a lot of radiocarbon. It turns out there was a massive solar storm between 774 and 775, and this provided one anchor point to count from. It was also possible to match the unique patterns with those in very long-lived trees that are still alive or died in a recent known year, giving a modern anchor point to count back from. Working from these 2 points, the researchers were able to determine that multiple lakes were formed throughout the Puget lowlands between fall 923 and spring 924. Because the trees were dormant for winter, it isn't possible to say if there was just one quake or a group of closely spaced quakes. What is clear is the event was tied to a shallow fault capable of great destruction. This kind of a pair of events is particularly dangerous because the second quake will destroy anything destabilized by the first quake, while people are actively searching for those trapped in the wreckage. These trees seem to indicate that similar shallow faults are in the Puget lowlands. According to Black, quote, "These are 4 shallow faults that had shown evidence of having ruptured roughly 1,000 years ago in a cluster of earthquakes called the Millennial Cluster. For example, a 25-foot cliff was thrusted into the air from West Seattle out to Puget Sound. It also triggered a local tsunami and landslides that stripped mountainsides of whole forests and discarded them into nearby lakes, Washington and Samish." End quote. The linked nature of these 4 faults means hazard maps of the region need to be updated. There's no way to know when these faults may go off again. All we know is they can go off together. And the last time they went off, they formed some lakes and filled other lakes with forests. And that is just something we need to plan ahead for if it happens again. Our planet finds lots and lots of ways to wreak havoc on our lives. While earthquakes are fairly rare, other problems are just part of the weather. Consider lightning. The standard lightning bolt carries about 300 million volts. It can start fires, it can burn out electronics, and it can even maim or kill unfortunate individuals. But your standard lightning bolt is just a casual zap compared to a super bolt. Carrying more like billions of volts, super bolts can cause major damage to whatever they strike. Luckily, only about 1% of all bolts are super bolts, and they tend to cluster in specific places, including over the northeast Atlantic Ocean, the Mediterranean Sea, and the Altiplano in Peru and Bolivia, which is one of the tallest plateaus on Earth. Generally, lightning bolts can be detected from the bursts of radio energy they give off. With enough radio detectors, their locations can be precisely measured. This is where the worldwide lightning location network comes in. With 70 some odd sensors, this network can identify where, when, and how powerfully lightning strikes. According to a new paper in the Journal of Geophysical Research, Atmospheres, led by Avachi Ephraim, this data killed the theory that aerosols were triggering the lightning. Instead, they found that when storms are particularly close to the ground, the bolts can be much, much stronger. Essentially, shorter bolts face less resistance and can hit with a greater punch. Moral of the story? You want those thunderstorms as high up as possible. The normal 12 to 18 kilometer altitude for storms, that is good. When you see things closer to the ground, be afraid. Lightning is something we've observed on worlds ranging from Earth to Mars to the gas giants Jupiter and Saturn. It has been assumed even Venus should have lightning, but you know what they say about assumptions. When the Parker Solar Probe swung past Venus in 2021, they failed to notice any of the radio signals associated with lightning. This was the second time researchers failed to see lightning's signals. So maybe, just maybe, there is one less thing waiting to kill you at Venus. Maybe. More data is going to be needed. This work is published in Geophysical Research Letters and led by Harriet George. Up next, we're going to look at space objects shedding badly. Stay tuned. One of the wildest things about astronomy is the diversity of research problems that all somehow get grouped together as astronomy. In this segment, we're going to span the scales. Let's start with a star in the nearby Pinwheel Galaxy, or M101. Or should I say, former star. On May 19, 2023, Japanese amateur astronomer Koichi Itagaki spotted a bright point of light that hadn't been in M101 before. He reported his discovery and went the extra step of dropping an email to Japanese expat and supernova researcher Dashi Hiramatsu, who is a researcher at the Center for Astrophysics. Hiramatsu and Ito Berger had a new project set up to get observations of supernovae from a variety of telescopes as soon as they were reported. This new supernova, cataloged as SN 2023 IXF, was primed to be their first target. As Berger reports, quote, Supernova 2023 IXF exploded exactly at the right time. Only a few days earlier, we commenced a new ambitious 3-year program to study supernovae explosions with a submillimeter array, end quote. With explosions like supernovae, different colors of light are emitted at different times as the explosion evolves and interacts with its surroundings. The timing of new light appearing and fading can reveal details in both the explosion and how it affects its environment. Berger further explains, quote, the only way to understand how massive stars behave in the final years of their lives up to the point of their explosion is to discover supernovae when they are very young and preferably nearby, and then to study them across multiple wavelengths. Using both optical and millimeter telescopes, we effectively turned SN 2023 IXF into a time machine to reconstruct what its progenitor star was doing up to the moment of its death, end quote. And what its progenitor star was doing was shedding mass. Based on how quickly the area around the star started to interact with the supernova shock waves, the researchers believe the pre-supernova star gave off an entire sun's worth of material in the year prior to the explosion. 2023 IXF was roughly 8 solar masses when it died. Existing computer models described how massive stars run out of fuel for their internal nuclear reactions and then end up collapsing. It had been understood that these massive stars shined so bright that they blasted off some of their outer layers, but the amount of material indicated by these observations exceeded expectations. This means that this star, and possibly many stars like this one, suffered some kind of an instability that caused significant mass loss as the star neared death. This research, which included numerous observations within just a couple hours of the supernova's light reaching Earth, was only possible because of the existing collaboration between professional and volunteer astronomers. Hiramatsu explains, quote, the partnership between amateur and professional astronomers has a long-standing tradition of success in the supernova field. Without this relationship and Itagaki's work and dedication, we would have missed the opportunity to gain critical understanding of the evolution of massive stars and their supernova explosions, end quote. The complexity of astronomy shines bright in how hard it is to understand things as simple as stars. They're just balls of gas pulled together by gravity and held up by light pressure. You can vary a star's mass and you can vary its composition, but everything else is defined strictly by physics. Everything else is more complicated. And the complexity comes in countless different forms. Consider the galaxy. As near as we can tell, no two systems are alike. This diversity is particularly apparent in moderately sized galaxies that may show signs of recent collisions. In a newly released image from the Blanco 4-meter telescope in Chile, one murderous galaxy has been caught showing off the remains of a system it has consumed. cataloged as NGC 3923. This elliptical galaxy is the largest in a relatively nearby group. It is circled by 42 shells of material. In a typical case of obvious shape leading to obvious name, this is an example of a shell galaxy. This unusual structure is thought to occur when a smaller galaxy spirals into the larger galaxy and sheds stars as it is eaten. If you've ever dropped food coloring into frosting being mixed on a mixer, you may have seen a spiral of color getting created. This kind of spiraling of trailed stars is actually somewhat similar. NGC 3923 stands out among shelled galaxies for having the largest number of shells and also as having some of the most symmetrically shells so far observed. This image was taken by the dark energy camera, which captures 250 megapixels per image. Its large field of view not only captures all 42 rings of shed stars, but also captures a myriad of background galaxies and even stars in our own Milky Way. This is just an image release, but we can expect to see these images leading to research papers on NGC 3923, its shining shells, as well as papers capturing the science of the background systems that probe farther and farther into the universe. The constantly spiraling nature of just about everything leads to all kinds of different structures across many different scales. From the shells of NGC 3923, we now turn to the jets of galaxy M87. Located in the heart of the Virgo cluster, M87 is a giant elliptical galaxy with a truly massive black hole in its core. It's undergone numerous mergers in its long life, and relics of these events can be seen in deep images as dust lanes and patterns of stars. These mergers are also reflected in the presence of M87's massive jets. Material that is spiraling in toward the galaxy's core forms into a dense hot disk. This orbiting ionized gas in turn generates a magnetic field capable of firing material out of the galaxy. These are the jets we see on the smallest and largest scales when we look at this system. It was noticed several years ago that these jets appear to spiral out, but the details of the spiral weren't revealed until now. In a new paper in the journal Nature, researchers led by Yasu Chu analyzed 22 years of high-resolution radio images that followed the slow evolution of the jet's positions over time. Using very long baseline array data and data from the East Asian Very Long Baseline Interferometry Network, they uncover an 11-year cycle that seems related to the slow precession of the black hole's disk. This kind of change in tilt is a lot like the change in axis seen in a spinning top. This is an imperfect analogy, however, because your normal toy top doesn't experience relativistic effects. As objects rotate, they carry the space-time continuum with them, thanks to a relativistic effect called frame dragging. This can add to the precession of the system's axis as it rotates. It's a small effect, just a few parts in a trillion. But it's something we've been able to measure here at Earth with the sensitive Gravity Probe B mission, which looked at Earth's rotation and precession. Working backwards from the observed precession of the jets on M87, researchers can now say that M87's central black hole must be rotating. Collaborating researcher Kuziro Hado explains, quote, "After the success of black hole imaging in this galaxy with the Event Horizon Telescope, whether this black hole is spinning or not has been a central concern among scientists. Now anticipation has turned into certainty. This monster black hole is indeed spinning." End quote. Going into this segment, we promised two things. We were going to look at space objects shedding badly, and we were going to look at things at a variety of different scales. I think we've done a pretty good job as we've jumped from supernovae shedding mass to galaxies shedding stars to a black hole shedding particles through giant jets. We've covered a lot of scales, but not all the scales. In this last story, we look down to the small scales as we turn to Jupiter's moon, Europa. This moon is known for two things. In Arthur C. Clarke's 2001 A Space Odyssey, we learned all these worlds are yours, except Europa. Attempt no landing there. This quote from 1968 was an interesting teaser for Voyager's 1979 encounters with Jupiter, which revealed Europa is an ice-covered moon that might contain life in oceans beneath. In the 44 years since Voyager's visits, anything that could be pointed at Europa has been pointed at Europa, as a lot of us dream of a day when a perfectly sterile space probe is able to descend into that subsurface ocean. In recently released JWST images, the presence of carbon near the surface of Europa has been discovered. According to Samantha Trumbo, quote, "We now think that we have observational evidence that the carbon we see on Europa's surface came from the ocean. That's not a trivial thing. Carbon is a biologically essential element." End quote. Put another way, geological processes are causing Europa to shed carbon, and this lets us know that the stuff of life exists in its icy seas. This research expands on earlier work done by the HST. As Trumbo explains, quote, "Previous observations from the Hubble Space Telescope show evidence for ocean-derived salt in Taro Regio. Now we're seeing that carbon dioxide is heavily concentrated there as well. We think this implies that the carbon probably has its ultimate origin in the internal ocean." End quote. Exactly what's going on at the surface will hopefully be observed in the not-too-distant future. A year from now, in October 2024, the Europa Clipper should launch, and it is expected to reach Europa in 2030. I, for one, hope that in the material Europa is shedding, researchers are able to find undeniable evidence of life. Here's to hoping we're still here reporting when Europa Clipper gets to its destination 8 years from now. Up next, we're going to take a closer look at antimatter and at some new observations of how gravity interacts. Stay tuned. Antimatter is one of those things that sci-fi led us to believe would be much more of a problem than it actually is, sort of like quicksand. Turns out, I've never encountered quicksand, and I encounter antimatter all the time, and neither has actually tried to kill me. Here's the thing about antimatter. We get taught in school that when matter and antimatter mix, they annihilate each other and give off a whole bunch of energy. Sci-fi tells us that energy can power starships and destroy planets. What they don't generally teach us is matter and antimatter only annihilate each other when they match and interact. When an antimatter neutrino casually passes through your body, nothing happens. When an antimatter electron or positron goes through your body during a PET scan at the hospital, you and the city you're in, they don't explode. It turns out antimatter generally wants to only explore complete mutual destruction with its regular matter counterpart. And the amount of energy released is directly related to the amount of mass being destroyed. When a hydrogen meets an antihydrogen atom in the vacuum, they give off less than a billionth of a joule of energy. Let's put that in some context. A 1-watt light bulb gives off 1 joule of energy per second. This means you'd need more than 1 billion matter and more than 1 billion antimatter hydrogen atoms to light up a 1-watt light bulb for 1 second. And I'm not actually sure if 1 watt light bulbs are even a thing. A Christmas light bulb is 5 watts. So 1 antimatter hydrogen atom, totally not a concern. 1 billion antimatter hydrogen atoms, first of all, I want to know where they came from because researchers just aren't quite working at that scale yet. But if you somehow had 1 billion, you might get a noticeable shock, but you aren't going to get killed. And it is a big might on that shock. The energy released when the particle's annihilated recycles itself into new particles, in this case pions, very rapidly. The biggest problem with antimatter is it likes to escape. It's possible to trap charged particles using magnetic and electric fields. Neutral atoms, electric fields do nothing for them, and it takes super precise control of magnetic fields to be able to contain even a slow-moving antihydrogen atom. Well, antimatter atoms were created in the 90s. It wasn't until 2010 that the Alpha Collaboration Group at CERN was able to first slow the antimatter atoms down and then confine them using superconducting magnets. But once they figured it out, they just kept doing it. And this allowed one of those things we always say is true to actually be tested. For decades, the majority of scientists have been casually saying that matter and antimatter both react to gravity the same way. After all, these are both bits of mass mixed with charge, spin, and other nuclear properties. Antimatter particles just have the opposite charge, magnetic moment, and other properties of regular matter. These are merely two different families of particles, and we don't even really know why they exist in different amounts. So we assumed matter and antimatter responded to gravity the same. Relativity even gave us really good reasons to believe this was true. But there have always been folks saying, but what if it reacted just the opposite? What if antimatter had like an anti-gravity kind of a force? So now that the folks at the Alpha Collaboration have gotten really good at making and containing antimatter atoms, an experiment was possible. The team built a cylindrical containment vessel and placed magnets on both ends to confine the antimatter atoms, and then let gravity do its things. As described in the release on this work from UC Berkeley, quote, "If the bottle is oriented vertically, the atoms moving downwards will accelerate due to gravity, while those moving upward will decelerate. When the magnetic fields at each end are identical, that is, balanced, those atoms moving downward will have, on average, more energy. Thus, they will be more likely to escape through the magnetic mirror and hit the container, annihilating in a flash of light and producing 3 to 5 pions. The pions are detected to determine whether the anti-atom escaped upward or downward." End quote. And the light and the pions produced by the annihilating anti-hydrogen atoms lit the way to the answer. The majority of the light and pions came, as theory expected, from the downward side of the cylinder, indicating within error that anti-atoms are affected by gravity the same way as regular atoms, and making it clear that anti-gravity definitely isn't at play. This work is published in a new paper in the journal Nature, led by E.K. Anderson. As researcher Jonathan Wordle points out, quote, "If you walk down the halls of this department and ask the physicists, they would all say that this result is not the least bit surprising. That's the reality. But most of them will also say that the experiment had to be done because you can never be sure. Physics is an experimental science. You don't want to be the kind of stupid that you don't do an experiment that explores possibly new physics because you thought you knew the answer and then it ends up being something different. End quote. And now we know. Antimatter falls in gravity and isn't nearly as much of a hazard as sci fi led us to believe. Up next, we're going to look at some new tech, and we'll be joined by Eric Mattis for Tales from the Launchpad. Stay tuned. I want to start this story by saying there are a lot of different kinds of artificial intelligence. Some AI, like my Siri, look for patterns in our behavior and try to serve us up information related to those behaviors. For instance, my devices learned I use the NPR app all the time. And when I ask them to play the news, I get the latest from NPR. There are times when Siri completely screws up, but it is taking what it generally knows about people and what it has specifically learned about me, and it's doing its best. And honestly, I don't know what I'm doing sometimes either. I'm juggling a lot. And Siri tries to juggle a lot too. Luckily, this mistake-prone kind of AI isn't the kind used for most science. For science, we try to keep things much more specific. A machine learning algorithm might get shown 500 images of dogs and 500 of cats, and then be asked to label images as dogs or cats. They might get trained to identify kinds of galaxies or to find craters on the moon. In every instance, the algorithm is shown a multitude of examples and asked to then repeat the classifications based on whatever factors the computer senses can key in on. We don't always know what the computers are using to make their choices, but it turns out computers can be fed a lot of examples, and they can learn from those examples to replicate the choices they were trained on. Since we aren't always sure what computers are looking for to make their choices, it can be hard to know what they can accomplish with what they learn. For instance, researchers recently asked, can we train software to identify things that were and weren't ever alive? It turns out the answer should be yes. They fed samples through a gas chromatography mass spectrometer similar to the one on Mars Curiosity rover. This device separates the samples into their components and measures over time the intensity and mass of the components. For their training data, they used 134 samples rich in carbon that came from recently living cells, age-degraded samples, geologically processed fossil fuels, carbon-rich meteorites, and laboratory-synthesized organic compounds and mixtures. 59 of these were of biological origin, biotic, such as a grain of rice, a human hair, crude oil, etc. 75 were of non-biological origins. According to the results presented by Robert Hazen at the Goldschmidt Geochemistry Conference in Lyon, this training allowed the algorithm to separate biological specimens from non-biological specimens 90% of the time. What's more, it was able to say if the biological samples were recently alive or fossilized life. According to Hazen, quote, there are some interesting and deep implications which flow from this work. First, we can apply these methods to ancient samples from Earth and Mars to find out if they were once alive. This is obviously important for looking at whether there was life on Mars, but it can also help us analyze very ancient samples from Earth to help us understand when life first began. It also means that at a deep level, biochemistry and non-biological chemistry are somehow different. End quote. This was a preliminary presentation of these results. I hope that as future papers are published, we can learn from the machine how it sees life. As always, we remain hopeful that fossil hunting on Mars will happen in our lifetime. Next up, I'm pleased to welcome on aerospace correspondent Eric Mattis for this week's Tales from the Launchpad. Hey, Eric.
Hi, Pamela. Not a lot happened this week. just a Starlink launch and classified launches by China and Iran. So we're going to tell you a bit about NASA's upcoming Psyche mission. Psyche will be an interesting mission. It's the first NASA payload to launch on a Falcon Heavy and the second Falcon Heavy to launch a payload beyond Earth orbit. In this case, it's going to an asteroid named Psyche, which orbits the Sun at about 2.9 times the distance that Earth is from the Sun. Assuming that the launch is successful, it will spend 3 years in orbit around the Sun, lining itself up for a Mars gravity assist in May 2026, which is 2 years later than originally planned when it was scheduled to launch last year. That launch didn't happen because of significant issues with the spacecraft's computer that were discovered about a month before launch. The problems were fixed, however, they missed the launch window, hence why they're only launching this month. There was concern that the recent threat of a government shutdown would have delayed the mission even further, but as it turns out, would have been exempted, meaning the workers preparing it for flight and activating after launch would have still worked, but without being paid until sometime after the government started back up. After the Mars flyby in 2026, it will arrive at Psyche in August 2029, with the mission ending in 2031. Scientists hope to discover the secrets of the early solar system by examining this large metal asteroid up close. And once the Psyche mission has launched, we'll tell you about it in a future episode of Escape Velocity Space News. Just before we recorded this episode, Virgin Galactic's Galactic 04 flight carrying 3 passengers with 3 crew members took place. On October 6th, at about 1540 UTC, Virgin Galactic's VSS Unity spaceplane was carried aloft by VMS Eve from Spaceport America in New Mexico. VMS Eve was piloted up to about 45,000 feet, at which point Unity was released about 35 minutes after takeoff. Once clear of Eve, the spaceplane fired its rocket to climb to just over 290,000 feet. The passengers on VMS Eve, Namira Salim from Pakistan, Trevor Beatty from the UK, and Ron Rosana from the US, were accompanied by Virgin Galactic's chief astronaut instructor, Beth Moses, and the spaceplane was piloted by Kelly Latimer and CJ Sturkow. Salim became the first Pakistani to go to space, and this flight was yet another bucket list item for this explorer, adding to achievements that include being the first Pakistani to travel to both the North and South Poles. She is also one of Virgin Galactic's founder astronauts, as she paid for her ticket about 17 years ago in 2006. The space tourist experienced a few minutes of weightlessness and got to view the Earth from space before returning to Earth, landing at Spaceport America at 1643 UTC. We keep track of orbital launches by launch site, also called spaceport. According to RocketLaunch.live, so far this year, the USA has had 78 launches, China 46, India, Kazakhstan each have had 7, New Zealand and Russia each have had 6, Japan 3, French Guiana, Korea each have had 2, and Israel, Iran, South Korea, and the United Kingdom each have had 1. Of these 160 launches, there have been 8 failures, reminding us that space is hard.
Thanks, Eric. Before we go, I want to take a moment to look back on the 53 minutes during which Venus had its first functional lander. On October 22, 1975, the Soviet Venera 9 lander touched down on the surface and recorded and returned a single image. This one exposure, just 115 by 512 pixels in size, showed a region of rocks and dirt and left us wanting for more. And we'd get more, a very, very little bit more. Between 1975 and 1982, the Venera program would return 10 images from 4 successful landings. It's been more than 40 years since we got an image from Venus's surface, but there is hope the wait is almost over. NASA's Da Vinci mission hopes to land a probe on Venus in 2031 with a system capable of surviving 17 to 18 minutes on Venus's surface. Luckily, modern tech can take and send photos a lot faster than Venera 9. Here's to hoping Da Vinci flies in June 2029 as planned. That's all for now. Good night, everyone, and remember to go out and look up.